Welcome to the first session in our NSF-NHERI Professional Learning Community webinar series. As a friendly reminder, all participants will receive an email after today's webinar sharing facility resources, contact information for each presenter, and a survey to share your feedback on your experiences today. So please keep an eye out for all of that information. In this first session, we will learn more about the NHERI large large high performance outdoor shake table at the University of California, San Diego. And we are joined today by their PI, Dr. John McCartney. We will follow his presentation up by the NHERI Cyber-Physical Simulation Facility at Lehigh University. And its PI, Jim Ricles, will join us. And then we will conclude today's session with the NHERI DesignSafe Cyber-Infrastructure Facility at the University of Texas at San Antonio and its Deputy Director, Tim Cockerill. But before we begin, we would like to share the format for today's webinar. After each 15-minute presentation, that facilities presenter will hold a 10-minute Q&A session. At that time, we invite you to enter your questions in chat or to raise your hand, and we will call on you to share your question. And then if you have further questions and we don't have a chance to get to all of them, please, please, please reach out to the presenter. They look forward to answering any questions that you have about the facility's capabilities, the resources, how you might move forward, writing a proposal using those facility resources. So we're super excited to share today John McCartney and the Shake Table at the University of California, San Diego. Before I hand it over, I just want to give a brief introduction. John McCartney is a professor in the Department of Structural Engineering at the University of California, San Diego. He specializes in geotechnical and geoenvironmental engineering. He holds the Hal Sorensen Endowed Chair and directs the Engelkirk Structural Engineering Center, home to the NHERI Large High Performance Outdoor Shake Table, which we're going to talk about in just a moment. His research focuses on unsaturated soil mechanics, geosynthetics engineering, and energy geotechnics, earning him several accolades, including Shamsher Prakash Award, the R.M. Quigley Award, and the Walter L. Huber Research Prize as a significant contributor to ASTM and ASCE Geo Institute. He has also served as co-editor-in-chief of Computers and Geotechnics and in many editorial roles. Dr. McCartney earned his BS and MS in civil engineering from the University of Colorado Boulder and a PhD from the University of Texas at Austin. Welcome, Dr. McCartney.
Thank you, Robin. Can you hear me okay?
Yes.
Great. So I'm happy to talk with you this morning to tell you a little bit about the large high-performance outdoor shake table that we have here at UCSD. And you see two different acronyms there, the LHPOST. This is kind of our historical facility that was a one-dimensional shake table, and LHPOST6, which is our latest reincarnation, which can now apply 6 degrees of freedom earthquake motions. So we have a very large team here at UC San Diego. I've been the PI for about 2 years, but prior to that, Professor Joel Conte was our PI for almost 11 years. He has stayed on after his term as PI as one of our co-PIs. So we have a good continuity of past knowledge. We also, on our team, have Michelle Morrison, who helps with site operations. Alessandro Palermo is a new co-PI working on site user services, and Lily Van den Einde works with our outreach and engagement. Karush Lafizade, he's the person that, if you're a new user hoping to use the facility, he's the best contact to reach out to right away. He's our site operations manager. He now has a lot of experience on the site, and we have some great staff that have almost 30 years of experience working on the facility. Abdullah, Alex, Bucky, Eduardo, and Robert. And we have a couple of previous PhD students that have graduated and moved on to working at university and practice, but they have a lot of simulation tools that they developed over their time at UCSD that we're still relying on. And then, so if you plan to use the shake table in the future, there's no need to involve CoPI from UC San Diego. However, we do have several of our faculty in the department who have used the facility in the past and are available for you if you need help on getting your project started or answering specific project questions. So we call these capacity building partners: Tara Hutchinson, Gilberto Mosqueda, Benson Shing, and Georgios Zabris. So let me tell you a little bit about the facility. So this is the original facility on the left. The shake table, which we call LHPOST6, or LHPOST was the original version of it, is the main part of the facility. But we also have a large soil structure interaction facility with a strong wall that can be used to apply lateral loads to different geotechnical systems on either side of the strong wall. So we have two different soil pits. The hydraulic power systems building is where all of the hydraulic control systems for the shake table are located. And on the side of that, we have a blast or impact testing facility. This is what the site looks like now after the upgrade. It looks very similar, but there's a shroud around the shake table, which I'll show in some pictures later, that allows the 6 degree of freedom motions to be applied. So the vision for our facility is rooted in 4 different needs that are geared towards advancing the science, technology, and practice in earthquake disaster mitigation and prevention. First, we want to generate fundamental knowledge for understanding the systems level behavior of buildings, critical facilities, bridges, geostructures during earthquakes, from the beginning of damage to the onset of collapse, including the effects of soil structure interaction and the contributions of lateral and gravity load resisting systems, and also the behavior of non-structural systems within a structure. We want to generate experimental data to support the development, calibration, and validation of high-fidelity physics-based models for structural or geotechnical systems that will progressively shift the current reliance on physical testing to model-based simulation for the design and performance assessment of critical civil infrastructure systems. We want to generate data and fragility information to achieve the full realization of performance or resilience-based design, and then provide ultimate validation tests for protective systems, retrofit methods, and the use of innovative materials, components, or systems, as well as construction and manufacturing methods that can help protect civil infrastructure systems from earthquake hazards. So the LHPOST6, which was the original incarnation of the shake table, has a long history. There were 34 major research projects performed on the shake table between the period of 2004 and 2019. The facility was one of the original NICE network centers. And after that, it was part of the NICE NSF-NHERI network in 2016. So I'll show some pictures of some of these projects that have been performed using the LHPOST, the first reincarnation, as well as 5 major research projects that we performed since the completion of our upgrade. So this is our old system, so we don't need to spend very much time here, but you can see some key details. We had about 3/4 of a meter of stroke in either direction. So this direction X is the main direction of shaking for the table. Y is the transverse direction, and Z is the vertical direction. So originally we could only move in the X direction about 3/4 of a meter. It has a very large vertical payload capacity, 20 meganewtons, or 2,000 tons force, which makes it the largest outdoor shaking table in the world. One interesting thing is that when we designed the reaction mass for the shake table, it was designed to be a 6 degree of freedom shake table. So all of the concrete infrastructure below the ground was designed for the eventual upgrade, even though initially we only had enough funding to have these horizontal actuators to provide the horizontal motion. The original LHPOST had very good tracking performance in capturing earthquake ground motions. You can see the acceleration time record, even when we zoom in very closely, we were able to very carefully capture the acceleration trends and also the displacements. These are a few pictures of the different tests that performed on the table. The nice thing that you can see here is that there's a very wide range of different projects. There are projects that extend the dimensions of the table. There are projects that rely on soil boxes. So we have a laminar container and a rigid container. There are tests that have large, very tall structures, like these transmission line towers. And then other ones that just have a very large specimen, maybe a critical piece of a bridge in this bridge column here. And also one other interesting thing regarding timber buildings, we've now tested a 10-story timber building, but when researchers came to get started on this, they first started with some smaller 2-story structures, going to a 4-story structure, and then using the information that they gained from those tests, brought it all the way up to the 10-story structure. In 2018, our site submitted an upgrade proposal to convert to the 6 degree of freedom table. It was designed shortly after that, and then it was constructed between 2019 and 2020. And since that time, we've done 5 projects. This involved a major overhaul of the control systems. So before the upgrade, we had a relatively small accumulator bank, which stored the high pressure oil that was pressurized by the pumps. And that pressurized oil went through the red lines and operated the actuators. The table originally was resting on pressure balanced bearings. And then those were converted to being vertical actuators that were not ported to apply vertical motions in 2009. And since that time, those vertical actuators have now been converted into full vertical actuators in our new system. And we've incorporated also, we now have 4 horizontal actuators in a V-shaped configuration, which allows you to apply motion in both the X direction as well as the Y direction. And then the 6 vertical actuators are able to apply the Z motions and also ensure that it's able to slide in the X and Y directions. We had to upgrade the accumulator bank. So this is a major upgrade here inside of our hydraulic control building. So we have 10,000 gallons of pressurized oil at 5,000 PSI that are sending oil to the different actuators in the system. The duration of the motion is dependent on the amount of oil that is stored inside of these tanks. If you're planning to do just a single degree of freedom motion, you can have a longer duration motion. If you have all of the different actuators being used, the duration starts to decrease. It's very important to ensure that this platen does not hit the sides of our reaction mass, and the critical locations for this are in the Y direction. So we have these bumper systems that prevent the energy from the table moving, from crashing into the reaction mass. These are filled with several different pins that would buckle, and they're able to absorb a large amount of energy in a very short displacement. Hopefully we don't need to use those bumpers, and we built ensure that everything is safe within our control system. We also have these hold down struts that provide the overturning moment for the shake table. So when you apply the large horizontal movements, that the table's able to stay plane. And those are basically nitrogen gas filled vertical cylinders. This is a picture of the top of the table after the upgrade. You can see these shrouds here. These need to roll along with the table during motion. When we activate the table, it actually lifts up by about a half of a foot. And these shrouds need to lift together with it. So there's hinges along the sides, and then there's rollers along the edges. So that all moves together with the shake table. These are just some of the performance specs. So in our X direction, we're able to actually have a greater displacement range due to the V-shaped actuators. We have a smaller displacement range in the Y direction, and then a little bit smaller than that in the Z direction. And the table is able to apply the three translational directions as well as the three rotations to have a full 6 degree of freedom motion. Even after the upgrade, there was a very strenuous performance calibration of the table, and we're able to capture the motions of these very accurately in terms of both acceleration and displacement. The Z direction was the most challenging one to capture, mainly because the table is pushing upwards only and does not pull back downwards. But even with that capacity, it's able to have a very good match to the target motion. There's a couple of videos here just to show these. We may not watch all of them since we have a short time to present today. This is a real triaxial ground motion from Iran. So this is without the shrouds around the edge of the table. You want to have the shrouds there to protect your actuators from material falling during the test, potentially. Let's go to the next one. This is a synthetic 6 degree of freedom motion. Sorry, this Iranian motion is only 3 degree of freedom translational motion. There aren't a lot of recorded synthetic 6 degree of freedom motions, so this was a synthetic motion. It is quite impressive, the movement of the table. If you get seasick, this is probably not a good video to watch. So I won't wade through the entire thing, but you get the point that it's able to move in all 6 degrees of freedom. As part of the facility, we have different other testing resources, soil boxes that you can use, a shared use modular or reconfigurable test bed building. We call this MTB2. And also we're hoping to build a universal base frame in the future to extend the base width available platform dimensions. We have 2 containers, a laminar shear box. This provides the shear beam boundary conditions to a soil layer. At the moment, this is only a one-directional laminar container. In the future, we're planning to upgrade this so that it can have both X and Y movements. And then we also have a stiff soil confinement box, which may be appropriate for something like a buried tunnel or a retaining wall within that box. That has a height of 7.6 meters. This has a shorter height of about 4.7 meters. And these are suitable for testing the seismic response of a range of soil foundation structural systems. So the MTB2 building, this is a steel frame building that can be put together and taken apart easily. And it can be configured in different ways to test different low-cost testing of components and systems under the multi-axial base configurations. So we can use seismic protective devices, lateral force resisting systems, or other non-structural systems incorporated strategically into the building to achieve your research goals. So this was the first test that performed on the shake table. This was sponsored by Corebrace. They had configured the building in 2 different patterns to see the behavior of that building. So this can be assembled and disassembled as needed. In the future, we're hoping to build a universal base frame to address some of because people sometimes want to test wider structures, like you can see here, without having to build outriggers for your structure. This is a parking structure and a warehouse bay. So in the future, this is kind of a conceptual design of what we're planning to extend the footprint so that we can look at structures with complex geometries, multi-bay frame buildings, or interacting buildings with a common soil media. Maybe that 2 buildings next to each other, potentially. So with the 6 degrees of freedom, I think we've enabled a lot of different types of testing. We can look at the combined effect of realistic near-field strong translational and rotational ground motions on both structures and soils. We can use the table to study inherent damping in structures and figure out what the best damping models are. I'm not going to go into detail due to our short amount of time. There's a lot of different opportunities for dynamic soil structure foundation interaction systems, looking at kinematic interaction, inertial interaction, verification studies under multi-axial excitation, soil box studies, and potentially real-time hybrid shake table testing in the future. The boxes are suitable for reinforced soil systems, retaining walls, tunnels, slopes, and then also for looking at geotechnical issues that you can't look at in a laboratory scale. So gravel that has large particle sizes, tire-derived aggregates that have large particle sizes, and then systems that involve a large amount of settlement of the soil that you couldn't capture in a smaller scale test. The table is suitable for looking at unreinforced masonry buildings, seismic performance of reinforced concrete or reinforced masonry wall structures, structural concrete and precast concrete systems, steel systems. These have all been studied in the past, but there's still more opportunities to look at these under 6 degree of freedom structures. These commercial tilt-up buildings are being used more in practice, and they didn't behave well during some of our past earthquakes. Looking at non-structural components and systems, this has been a theme of many of our recent projects. Advanced and innovative earthquake protective systems and innovative building systems, wood, masonry, concrete, and steel. We also are working on energy power structures. One of our recent tests was looking at the dry storage casks for nuclear waste for Sandia National Laboratory. With the universal base frame, we could potentially look at bridge structures, incorporate different sensors to look at structural health monitoring during earthquakes, during and after earthquakes, and then enable this full realization of performance or resilient-based design. So just a couple videos of the recent projects. I'm not going to show all of these due to the short times, but this is the Tallwood project. So a 10-story wood structure. And you can see that when they built this building, they looked at different components and the different directions of shaking. They worked with different vendors to look at different facades on different sides of the building. So when you're building something so large, and also like a staircase, structural behavior of the staircase, they wanted to get the most bang for the buck. Some of these projects lasted a full year on the shake table before they started to test. So it's good when you're able to add on to a lot of these projects. These are just some of the results from that study. After that, a 10-story building, the top 4 stories were removed, and they tested a 6-story building and added some different components, a steel frame into there, adding different braces. And it was the same structure, but a different research team that worked on that. So there were a lot of interesting aspects that were added on. The most recent large structure was the cold form steel 10-story building that was tested by Tara Hutchinson and Ben Schaefer and Cara Peterman. And this looked at a slice of a real 10-story archetype building made out of cold form steel. This video is available on YouTube. You can watch it later. I think there's music. I'll fast forward to the interesting part. So they had a lot of non-structural components on the top of the building to evaluate their response. So this was all built modularly. They had one site that was built conventionally and the other site where the different parts were lifted into place. You can see here. So looking at different construction techniques and the effects of earthquakes on those. Okay, so I think I'm running out of time, so I just wanted to say that we're here for you to help with planning your proposal. Our website has a lot of details and documents that you should look at to help you in your planning. We definitely recommend that you discuss with us during your proposal preparation to make sure that the project is going to be feasible on the table. We always say that construction and demolition of the specimen are the responsibility of the researchers. Our operations budget is there to help do the test, provide sensors and sensor installation, and then also giving you the data that are obtained during the test. And we also have staff that are available to help with certain construction issues. We keep everything confidential as you're preparing your proposal, but we're here to help you prepare and plan the advancement of your unique ideas, and we really want you to be successful. We don't have a user research workshop planned at this moment, but this is another very useful way for you to come and see the facility physically and get involved. I wanted to also just put this here, so if you're planning to do a project, you may not have all of these details when you're at the proposal stage, but once your proposal gets funded, it's good for you to get organized and make sure you have drawings of what you want to test, your plans for building and demolishing the building, your draft instrumentation plan. We need to make sure that we have enough sensors and types of sensors for your particular tests, and then what ground motions you plan to use. So we can run these through some of our software to make sure that they will work. And then we do have a busy schedule usually, but we're able to, if you tell us when you want to start and end the test, we can put it into our calendar and work with you to get everything working. Our website, again, has a lot of useful information, so please go to these links. They're available in the PDF of the presentation. But with that, there's also some publications that you can look over to get more details on the performance characteristics. And please reach out to Krush or myself first when you want to learn more about the facility. But with that, I'm sorry I went a little bit long, I think, but I'm happy to answer any questions.
Yes, I think you have one that is in chat. I'm going to ask that you would answer that in chat so we can go ahead and stay on time with our target with Jim beginning. But thank you so much for coming and sharing that wonderful presentation with us. If you have questions, I did put Dr. McCartney's email in chat. We will share this presentation with you. It will be available on NHERI platforms. So thank you so much. At this time, I'm going to ask Dr. Ricles to go ahead, and if you will hold for just a second, I'm going to introduce you and we'll go ahead with your presentation. Again, thank you so much, Dr. McCartney. And if I can find. All right. So continuing on with our next site, we are excited to learn more about the NHERI Cyber-Physical Simulation Facility and meet Dr. James Ricles. I want to first introduce him. Dr. Ricles is the Bruce G. Johnston Professor of Structural Engineering at Lehigh University, where he also serves as the Director of the Cyber-Physical Simulation Facility. With a PhD from the University of California, Berkeley, his research focuses on the behavior and performance-based design of structural systems under extreme loading conditions, including seismic and wind forces. A registered professional engineer, Professor Ricles is actively involved in advancing structural resilience and has supervised numerous graduate students. He has published over 634 peer-reviewed articles and received multiple prestigious awards for his contributions to the field, including the AISC Special Achievement Award and the NSF Presidential Young Investigator Award. With that, thank you for joining us, Dr. Ricles. I'm going to go ahead and allow you to share.
Okay, yeah, thanks, Robin. Those awards I should mention, I supervise the students. The students had tremendous contributions to that, and it's because they had access to good resources. So you probably see something you don't want to see, which is a directory, but I have two screens in front of me, and I'll want to wish everyone a good day. I don't know whether to say good morning or good afternoon, but here it's the afternoon. I'm on the West Coast. Let me try to get this. Can you see the screen okay, my presentation?
Currently, we see your notes.
Okay, hang on a minute here. It's the wrong thing. Sorry. I'm wasting time here. This system is very temperamental. Okay, so you should see everything now.
Yes, sir.
Okay, yeah, thank you. Yeah, thanks, Robin, for that nice introduction. And again, I want to wish everyone, hello. And this is, I think, a very nice opportunity that the NSF and NEES, the coordination office, has provided us to present our facility, which is open access. So our niche is cyber physical, and we used to call it real-time hybrid simulation, but hybrid sounds like a car running on a battery. So no disrespect to that, I'm going to refer to cyber physical. And so outline my presentation. I'll give you a little bit of an overview in terms of the facility, the infrastructure, some experimental protocols, and like what John just showed, Professor McCartney, some selected projects. I think it's important to see that, and then some proposal preparation resources. So what is the NHERI Lehigh EF's experimental facility? We're unique in that we offer things that are specialized. We have a portfolio of equipment, instrumentation, infrastructure, test beds, and experimental simulation protocols for large-scale multi-directional simulation. Some of this stuff is 43 years in the making. It took some effort, but we've evolved over time. And this is our laboratory, the day that it opened, which was 1987, and it's, of course, been filled since then. Now, our focus is on large scale. Multi-direction. This is a multi-directional reaction wall. I'm not sure you can see my pointer. Can you see the pointer floating around the screen?
Yes.
Okay. So this is a reaction wall, reaction floor, allows us to do multi-direction. Our focus includes nonlinear. Why nonlinear? Because extreme events, which you want to try to create resiliency for or against, systems may go nonlinear, material geometric. Now, what we do, I'm going to go back to calling it hybrid, which is really cyber physical. We perform such simulations that combine, and I'll show an example here in a moment, combine physical experiments with computer-based simulations, including AI, for the purposes performance assessment of large-scale components and systems. My own background, I have a professional engineering license, and I try to approach this where I want to create a tool for users to solve a problem, and that is then a problem that we try to come up with a solution rather than come up with a solution that try to find a problem that fits. Here's our staff. I'm the PI. I also direct the lab, so I don't have to argue too much with trying to assign space because I have authority to do both. But we have a lot of projects that coexist. Claudia Reese, she's she's coastal co-PI. Richard South, my colleague, is also structural engineering, and that's the senior staff. We then have Joe Saunders, our operations manager, professional engineer, registered engineer. He's also got a PhD in structural engineering. Ian Hoskins almost got his PhD. He's our Atlas research engineer. His specialty is fatigue and fracture. Thomas Marilla, any IT question you have, we have to do a lot of IT. Thomas is the person, and Derek is the one that runs the laboratory, oversees our staff. We have 8 staff, and Sandra lets us know if we're running out of money. She's our financial manager. She's a great person. They're all great people. Now, what are some important aspects? And I'm going to point to these because we've thought of this when we created our facility. Our facility has been in existence since 2002. And so scale effects are important. So you need to think about large scale test specimens, multi-directional effects, very important. You can have material geometric nonlinearity, so you want to account for that. Likely everything is load rate dependent, depends on to what extent. So you can have materials or devices. Devices could be dampers that you're trying to enhance a system against some event. So you add devices such as dampers to alleviate some of the vibrations. Now, when you do this, you need to account really for the system. You can't just isolate a component or ignore the soil structure interaction or the fluid structure interaction. So you have to have a synergistic approach. This is called multi-physics. What's multi-physics? Air, water, solids, fluids, heat. Those components need to account for so that it's really the real environment. And there's an issue with scaling laws. They're incompatible between the different physics. So if you do reduced scale testing, could be a problem because not everything scales according to the same law. It's usually time is the problem. And so also you have to be able to relate to a hazard. If it's earthquake return period, I guess wind the same thing. If it's, I guess most storms are return periods, but you have to relate to the hazard level so you can look at the performance-based design and make sure your objectives are met. And you got to be able to accurately represent the system, the loads on the system, you know, both spatial and time. And they have to all be synchronized. Otherwise, it's catastrophic. And this is just an example. This is a multi-directional timber shear wall system. You saw the 10 stories. This is the first story of a timber shear wall, but there's walls above this, stories above this that are virtually modeled. This is just the first story. You can see this is bidirectional, just predefined motions, the wood's being damaged. And when you look at the bidirectional, compare that with unidirectional. This is the out-of-plane base shear, in-plane base shear. Walls are designed to take in-plane, but guess what? They're going to be going out of plane as well because of the orthogonal effects and bidirectional ground motion. So big deal, right? The fragility drops by a factor of 2. You're likely to double the likelihood of exceeding critical limit states. It's shown right here. This is data based on these multi versus unidirectional tests. And so that it's just an example. So I just want to mention, like the shade table, multi-directions, it's very important to be able to accommodate this. And our facility can do so, and we focus on cyber physical, but that's not the only thing that we do. We like to also have other forms of testing, which you'll see some examples. So here's some of the equipment capabilities. It just shows cartoons or pictures of this, but I'll show you some specs. We have large force capacity dynamic actuators. They're the blue cylinders here. They're all hooked up to a damper. We've got advanced instrumentation DIC systems. This was a coupled shear wall system. The lower 3 floors were physical. The upper 5 floors were numerical. Here's the digital imaging on the deformations. The reaction wall and floor you've seen. We have real-time computing. This is one of 2 control rooms. And we have several large-scale test beds. That's a test bed. Here's a 4-story self-turning moment-resisting frame that was placed in this test bed and was subjected to earthquake load. And you can see the size by the people that are walking around here. Some reason this person's scratching their head. I'm not quite sure. Something may not have worked, but I think we resolved it. So this just shows you the actuators again, but about the capacity. This is where we're kind of very unique. 2,300 kilonewtons. You know, convert that into kips. About 500 kips. What's the speed? 1.14 meters a second. That's with 3 servo valves. You can go to probably 1.3. You say, well, how do you come up with these numbers? We've done numerical simulations to try to study what are the velocity and force demands on devices or stories that you're trying to exert motions on in the test. And so we came up with these demands. We found since then, sometimes you have to double the 2 actuators, like behind me on my wallpaper. That's a 2 million pound experiment where we had to put 2 actuators side by side because we need to supply 1 million pounds at each end. So we're able to rearrange this equipment. These are all servo valves with all the hoses. A lot of oil flows here. The DIC, you can have a range of resolution, 0.05 to maybe 100%. And then the control rooms here, there's 2, but they're linked. One controls the learning laboratory, the cyber-physical laboratory, and the other is the traditional control room. This goes back to the NEES days. So we do real-time, you know, multiple control, integrated control systems. We use ScramNet to get fiber optics to link all these workstations together, which I don't have time to go through. We did not take open Cs, no disrespect, and just piece it together. We developed everything from scratch. We had to do this because everything had to be interfacing, connected. And the analogy is if you drive a car from California to Bethlehem here in Lehigh and you get stuck in New Mexico, you'd panic unless you built that car yourself. No problem. So we can adapt. And so we have not only explicit finite element models because you don't have to iterate, same thing, integration schemes with control numerical damping, actuators control. I think John could attest to this. It can be a headache, so you know we have to have adaptive servo control, and Sometimes you don't have enough devices that you want to put in the lab, so you have to update those with nonlinear models, and we also use AI quite a bit. You'll see some examples. This is one of the several test beds. We have others you can see on our webpage, which I'll get to in a moment. This is our learning laboratory, available for also research, pilot studies. When we have researchers come, they can do pilot studies and actually get data for proposals. We use it also for training and hands-on, as well as workshops. And this smaller actuators, because they'd be reconfigurable. These are test beds. They still go pretty fast. You can see the speeds here and the capacities are up to 55 kips. And then we have a shake table. So we're not competing with San Diego, we're complementing San Diego. This is the mini version of the macro version at San Diego, but it's multi-directional. This is particularly used a lot for isolation of equipment in buildings. We just had someone doing some shake table testing for equipment in data centers in which it was seismically isolating the equipment. So the protocols, I first want to be very brief here, explain hybrid simulation or cyber-physical. So if you're given the challenge of evaluating the performance of this tall structure, 40 stories, and you say, yeah, sure, no problem, I'll just put it in the computer, I've done this many times. You sign the contract, and then you take the wrapper off and you say, uh-oh. NL, that's not National League, this is baseball season, but NL stands for non-linear dampers. And you ask, what are these devices? And the person says, I don't know, they're brand new. We want to see if they're going to work and make the system perform better. So that tells you, you probably can't model these analytically and do a full fine element analysis. If you say, that's not a problem, I'll test it, but this is 40 stories tall, and these devices probably shouldn't be scaled down because it will affect the response. So what do? Well, you split it. You model what you can model well with high degree of confidence, called the analytical substructure. What you can't model with confidence, you model physically and at full scale. Now, the two need to talk to each other because they're interfaced here, right? So that's through the simulation coordinator, which solves these equations of motion at each point in time for a disturbance. And what it will do is it will send out commands to each of these, and it will ask for its response. And that allows this equation basically to be integrated and you go forward in time. And you'll find a lot of references in the handout that was provided and also online here on our website that describes this in detail. And if you go through this for one time step, you go to the next and do it in real time, you have the real-time response. If you want to slow it down, that's fine. If you want to do wind loading where it's predefined, we've done this getting wind tunnel data, you just redefine the forcing function. We've got aeroelastic. We can do that as well with FIU. It evolves a little bit more, and I don't have time to go through this. But what I want to mention is the time steps. They have to be proportional to controller speed. And so these time steps are typically maybe 2/1024, or maybe 3/1024. You have very little time to do things. And that's where the explicit nature of all this has to be really considered, the development. Here's one of our big soil boxes here, a person. This is what, about 15 feet tall. Shake tables back there. That cyber-physical learning centers right here. We can do various types of hybrid simulation. They're all listed here, all the way from local, real time, slow down, do online model updating. We have multiple experimental substructures. We could do geographically distributed viewer facility. We've also, done this in many different forms. We could do predefined, or you could characterize devices, and dynamic testing as well, where it's predefined. Tsunami, surge debris, soil structure interaction, and also fluid structure interaction. Here's one example of multi-physics. So there's a wind turbine, there's a monopile put in the soil box. Everything above it, above the mud line, was modeled analytically, including the wave loading, the wind loading, the mechanical loads from the wind turbine. This shows the interface of all this stuff. So we're able to do that as well. Right now, wind turbines is not that popular, but we can do other forms of testing like this. And it will come back, I'm sure. So let me just finish with some research projects. This tall building, the idea was to see how well this building could perform or improve its performance with these dampers in the outrigger. There's going to be some noise here on purpose. This is a real-time test. This is the damper position right here. The other damper is modeled numerically, online model updating. I don't know if you can hear me.
Yes, we can hear you.
Yeah, so these are the BRBs that we're modeling every one of these members. It's very important because you want to do performance-based science. You have to know what every member is doing. These are braces in the bottom floor. They're yielding going nonlinear into the earthquake. This is the damper. It's the retigator is nonlinear. This is looking down at the roof and seeing it move in the east, west, north, south. Every 10 floors, we have the motion plotter, but we had every floor here, 44 stories. I think just had 10,000 degrees of freedom. East, west, north, south direction accelegrams, and that was the actuator of the one damper. And if you say, well, I'm interested in wind tunnel testing, we decided to put it TMD, tune mass damper, in this direction. And you only see the damper, the friction part. So where's the rest of it? The mass and the parallel viscous damper modeled virtually. This is the east-west direction, the viscous damper and the outriggers north-south, and the wind comes from the north and is going in the northwest direction. So you see the structure there's vortex shedding, and it's displacing in that direction, and then static and then dynamically oscillating because of the vortices. The braces remain linear. This is a very difficult damper to model. It's right here. You don't hear the sound because I'm sped this up because it's about 350 seconds. This is something that Leanne Cow, I know, was online here, had a lot of work to do. He was one of our research scientists that we've trained so well. He has a faculty position now, so we have some really good people. This is the damper. Now, to finish with soil structure interaction, if I try to consider soil, you can model it. You know, there's some constituent routines, very computation intense. This would be a fine element model. There's soil columns here I think, John, you could attest this to avoid trapping energy in the system. You know, it would dissipate out, kind of radiation damping. How are you ever going to do a real-time hybrid test? Because we have dampers here. This is a moment frame. We want to evaluate this. Well, we replaced the soil foundation of the neural network. So this is what we've done, the citations down here. If you just type my last name as engineering structures, you'll find this paper, and we basically replaced the soil foundation. The other parts are somewhat similar. There's model updating using common filter, but you see the other things, look what we had before. So the issue is, what is difference does the soil make? Before I get to that, you know, we do nonlinear modeling, you know, 2D or 3D. Here's the Atlas report for the software that we use. And we have to get soil response. So we use OpenSeas in 3D and 2D to get the training data for these neural networks, and a lot of degrees of freedom. So we work very closely with TAC. You know, Tim Cockerill has been very good to us in giving us computer time. And of course, we acknowledge that. So we've been able to produce the training data. And this is important. So you say, well, how important is soil? This is the hybrid test, these gray lines with no foundation, just fixed. This is the damper force deformation, moment curvature. Right here, this analytical model, this is physical, this is a roof drift. There's a floor diaphragm here at the top of the roof. This is the roof, I'm sorry, that's roof acceleration. This is the roof drift, and then the ground acceleration. You look at this fixed base, no residual drifts. The design procedure must work. Let's do the simulation with the soil. That's the blue curve. And if you told the owner to get a damper of about 400 kilonewtons and a stroke of about 30, you're going to be in trouble, because with the soil, in this particular case, there's a lot of soil structure interaction that it causes greater demand on the damper and also on the members. You see that artillery now is about 8 compared to what it was before. It was 2, and there's residual drift. So we're able to accommodate those effects here. And then storm surge. Again, we've done that. There's a paper that's published in Engineering Structures. I think it came out maybe this month. You can just go to Engineering Structures, just look up my last name. We've modeled the fluid with neural networks because computational fluid dynamics took 100 hours to do one computational fluid dynamics simulation. We had to do those to get the training data. But once we had the training data, we could run this in real time. That's a storm. We ran it for 30 seconds. It ran in real time by defining the fluid. And this is in an explicit form, is so we can do that because we know that the future, so to speak. And so this is just another component here. The idea was to look at output here. So everything else is modeled discretely or physically here. And then this is from one of those simulations. This is a reference here. You can see the vortex shedding here, the vortices. This is the tall building with dampers here under wind loading. Here is the dampers again. When TAC provided us the computational power to do this, and this is a replay. So if someone tells you neural networks you can't interpret, you can. You just do a replay where you take the boundary conditions from your simulation you got from the hybrid simulation, you use that as boundaries, and you put that into the original fine element model. You can get the interpretation. The reason you can't do that first, because the dampers themselves you can't model physically. So this allows you to do so. And then this is real-time model. This real-time modeling is cross-section, 108 fibers, there's 24 elements, 7 integration stations. That's real-time computing. Bidirectional loading at the base here, you see the damage. It's deteriorating both in strength and stiffness. This is the damper at the roof that we're able to have researchers use. These are tools available too. This is a reference here. And then there's shake table where this is the equipment, 3-story building. Here's the equipment. This is shake table. So the equipment's on top. It is modeled virtually. The building's modeled virtually. And here's the motion of the damper in 3D. The acceleration of the equipment, it's only 20% of the floor acceleration. So here, this data center, the equipment accelerations are significantly reduced. And what I want to leave you with is, like John, I think John did an excellent job, that I can just kind of lean on him a little bit. We have our website. If you go to our website, we have many tools that you can use for preparing your proposals. We have a user's guide, rates. Most things are paid for when we're sponsored by NSF, except for strain gauges and your specimen. But your specimen, you get donated, strain gauges students put on. Responsibility of cost is defined here. Data management plans, a template you can use. We have lab safety, very important. I have a checklist for both payload and original project you go through. And of course, you want to talk to us ahead of time, and it's confidential. If I sense there's a conflict of interest, I'll avoid it by not being in the discussion. We have a research scientist speak with you here, and this is the pre-proposal stage. You want to review these documents. There's also a list of facilities and equipment, other resources, and then that facility, that cyber-physical small lab. And then you had this handout. If you go to this QR code, you can get more information here. And with that, I'd like to thank you and also acknowledge NSF. Great opportunities. We've been in existence since 2002, like San Diego.
Thank you so much, Dr. Ricles. I think we have 2 minutes for questions. If you would like to put your questions in the chat, or if you would like to unmute.
I saw the last question, but I have to go to the top. I won't answer John's questions.
Yeah.
I'll leave those for John. Let me see. Where does my question start here?
I don't think there's questions in there quite yet.
Oh, okay, great. There's 9 questions, John. I guess you're going to be busy here. No questions yet. Okay. One thing we're going to do is, and there's a lot of synergy. I really suggest, as maybe you're thinking about questions, try to develop an approach where you can use more than one site to really look at something that's going to have an impact. You want to have a science question. It may involve more than one site, and NSF really endorses that. And what we've done, we have good relationships with San Diego. I've gone and visited San Diego. I know John. I know the other researchers there. I know people at the other sites. We've had projects where people have used both facilities, including the Tallwood. We did some of the component tests that you saw. You want to think about that a little bit. I think that helps make a big impact, and it's also collaborative and convergent type of research here. Let's see. Are we sticking to PIN, which is data-driven, or PIN? Well, yes, no, and no. The problem with physics informed. Unless the constituent routine is precise, you can get a bad answer. On the other hand, data-driven is not interpretive. You have to be able to do a replay like I showed. So we actually have done both. If you use physics, suppose you need less data. So Tim, we don't have to have as much computer time. You can use less data, but you have to be very, very careful. You have the right constitutive routine, and you're just using AI to run it faster. In our particular case, I'll encourage you, when you write a proposal, AI is all over it. Use AI as a tool to do something you couldn't do otherwise. NSF is looking to fund research like that, not just use AI because it's AI. And so in our case, we had to use AI here because we couldn't run those things in real time. So that's a good question. I don't know if there's any other questions, Robin. I may be out of time. I could take those later, I guess.
Yes, we've put in your email in chat. So if you have any more questions for Dr. Ricles about the Cyber-Physical Simulation Facility at Lehigh University, please contact him directly. We will also be sending out materials and resources that he has shared with us after we complete today's presentation. Thank you so much, Dr. Ricles. Dr. Cockerill, is it okay if I introduce you before you share? Thank you so much.
There we go.
Appreciate it. And okay. So again, thank you to Dr. Ricles, but we are also now excited to hear about the NHERI DesignSafe Cyber-Infrastructure Facility from its Deputy Project Director, Dr. Tim Cockerill. Tim Cockerill is a Program Director at the Texas Advanced Computing Center at the University of Texas at Austin. He currently serves as the DesignSafe Deputy Project Director, providing a web-based platform supporting natural hazards research, and is also the Systems Engineer for the Leadership Class Computing Facility Project. Dr. Cockerill joined TAC in 2014. And prior to that, he spent 10 years at the National Center for Supercomputing Applications at the University of Illinois. He earned his BS, MS, and PhD degrees from the University of Illinois and was a visiting assistant professor in the Electrical and Computing Engineering Department. After which he worked for 3 startups over 10 years before entering the academic supercomputing world. And we're so glad to have you here. Thank you for joining us.
Thank you, Robin. Thanks, everyone. Look forward to sharing about DesignSafe today. And of course, always happy to interact with you at any time on the Slack channels that we have set up for the whole NHERI program. Many of you probably are already participating over there. DesignSafe, as has been mentioned, and thank you, Jim, for the shout out about the TAC's supercomputing resources. So we have the privilege of being able to piggyback onto this massive supercomputing and data storage and data management capabilities at the University of Texas at the Supercomputing Center, along with 220 staff members at TAC, all full-time professionals. We are not faculty. About a third of us have PhDs. We have one simple mission, and that is support research. All kinds of computational research, and in this particular case, it is with the natural hazards community, one of my favorite projects that I get to work on. Why should you do anything with us, right? What is there really value in working with the NHERI program and DesignSafe and all of the partners? Absolutely. And all of us have impact stories available for you to show that we have a very strong impact across the entire natural hazards community and all of the network facilities that are involved here as well, and the Sim Center that develops computational applications that they run on our supercomputers at TAC as well. And this is just some information here to give you an idea. We are a very large community. We serve a very large community. We have a lot of data sets available to you. And as Jim mentioned, if you need if you're working in AI and you're looking for lots of data to do training on, we have a lot of publicly available published data available for you to access and use for your research, reuse in your research. The high performance computing, we have a lot of scientific applications that are available through the web, through Jupyter Notebooks, directly logging into the supercomputer, many different ways. I'm not going to talk a lot about all of the supercomputing capabilities and applications that we have available to you. Just know that it's not at all limited to what you see here or what you can get through the web interface. If you have other applications that you would like to run, you are welcome to, we may already support them on our high performance computing systems, or you can bring your own applications as well. And through the DesignSafe, through the NHERI DesignSafe program, we have some time set aside for your computational research needs, whereby you don't have to go through this national competitive process that you might normally do to write a small proposal and get time on the supercomputers. We have time set aside where it takes just a simple paragraph about what are you wanting to accomplish, and we can provide you with some time to get on our supercomputers, try them out, and oftentimes enough computing time to do all the work you need to get done. We support research from all kinds of different support that you may be receiving. You do not have to be funded by the National Science Foundation to use DesignSafe, to use the resources that we have available. Anyone in the world can log into DesignSafe and get access to the resources that we have available for your research. Also, and I'll talk about this a little bit more, but citing data is becoming much more common all the time. And you can see we've gotten over 11,000 citations of data from the data sets that are in the DesignSafe published data area. So that's why you want to come and work through NHERI, through DesignSafe, and be a part of it and add your data. And we'll talk a little bit about that as well. So in DesignSafe, we mentioned we have the data capabilities, data management capabilities. That's our data depot, the tools and applications, where we have all these scientific applications and data analytics and geospatial tools. For data discovery, you can do searching through the data depot itself, or the Recon portal has a map-based, location-based interface where you can look for any natural hazard events, earthquakes, hurricanes, storm surge, flooding, landslides, etc., that you may be aware of already, and go look there and see what data we have available. And we have links to other data sets around the country as well. And so there's just lots of ways to interact with our data, to bring your data to use the tools and applications. So why do you want to publish data? This is where I'm going to talk probably a lot about for the next, maybe 8-10 minutes probably, is make your data count, make your research reproducible, make your data reusable, do the work you're going to do with it, and that's great. But know that many other people could benefit from the data sets you produce, and that you can share your data sets, you can share scientific applications that you develop. We have a variety of data models that fit, and I'll show that in a little bit, fit the different types of data and help people to publish them in a reusable way, and also help other people discover them. So we encourage you to formally publish your data. We'd love to have you do it with us, but there are many other places to publish your data. And I will talk about the data models in a minute that are really your community's language. And we went out and we have our Dr. Maria Esteva. She is our digital data curator, and she worked with this community to develop data models that would be able to assist with, again, your ability to publish and someone else's ability to find your data. Publishing is formal. provides a permanent digital location, a digital object identifier, a DOI. It's not just a URL, it is a permanent location. Even if that data were to go to a different storage system, it would always point to that. Right now, we are the owners of that, and we are, at this point in time, responsible for maintain that. If for some reason in the future, things happen with NSF funding, someone else wins this capability to drive the cyber infrastructure side of the NHERI program, they would receive all of these DOIs. They would store all of the information, and your data would still be available. A DOI is essentially a contract. We are required to make this data available in perpetuity for others. So cite your data. That's very important. Just putting it in an acknowledgement is insufficient. We really need to have that, if you're writing journal articles, properly cited, just as you see here, like you normally would. And then in the references, you put the DOI and it looks something, put the reference, the citation, and it looks something like this, right? Okay, so in the data depot, under published, we have all these published projects, right? But we have these other storage areas too. What's important is My Projects is a place where you start. It's a shared space. It's shared with people you want to share with. It's private to the people you're sharing with until you want to publish. And you don't have to publish every piece of data that you put in there. You get to select what you want to put in there. You select your files, you provide some information, categorizing, describing, this is called metadata, and then it gets published, assigned a DOI, and it looks very familiar to a journal article in a lot of ways, right? It's got a title, it's got authors, it's got an abstract, essentially the description. And then there are many other benefits from publishing here, because we help describe the success or impact of your data set. And you can see here that how many citations has it had, and these will be described in a little bit. What is a unique request? What's a unique investigation? But I forget all the time. We have access to, or we have this right on the site here where it describes what does that mean, right? But this is people looking at your data or downloading your data. How many citations of your data have there been? We zip up all of your data into a single file so that someone could download the data set. And when they download it, the structure of it looks exactly the way it does here on the website, so that somebody doesn't get lost. It's not just a whole bunch of files and they can't understand where everything is. We maintain the structure that people see here. So here's the in-depth. When you click on details, you can see a lot of the information about what are unique investigations, what are unique requests. Just hover over the question marks, etc. there. So, so we give you a lot of information about the impact and success of your data sets being published. And then, and there's those definitions. Okay, so again, they're always there. But the main thing is getting your data published so that others can use it and you get the academic credit for providing those publications that others can cite. These are the different data models. If you're doing work at the experimental facilities affiliated with the NHERI project, like you saw earlier with the Shake Table and Jim's Atlas facility, and any of the other facilities and facilities that aren't part of the NHERI program as well, you can still publish any experimental project that you have, any data that you have available. Numerical simulation, again, if you develop some type of scientific application, or you're using some unique workflow across multiple applications, you want to share that information and how you did it, we have a data model for that. Hybrid simulation, which is what Jim mentioned, is the old description of that. He's using Cyber-Physical now. And Jim, maybe I need to put some information along there now. is what that type of project, data project is. Field research, reconnaissance work, or actually social scientists also use the field research project to publish their data in DesignSafe as well, and fairly new research software itself. So a numerical simulation, you might use established things like OpenSeas or AdCirc or some other simulation project, and describe everything you've done and share the output from maybe you did 1 million runs on our supercomputers, and sharing information and data sets from that. Research software is more of a sharing your code that you may have developed, and you can keep that code in GitHub like most people do, and still share it. And then we have a catch-all for other, you can publish without using a descriptive data model. This has to do with the research software. If you're familiar with GitHub, we do bring in all the things you would need, files you would need to really make that strong connection between your GitHub and the DesignSafe. Again, the reconnaissance portal, you can go through and find data. Most recently, we added an API integration to the Open Topography project. And so there you can discover data sets on Open Topography very easily, along with any other data sets we might have available through DesignSafe that we've had. Again, further discovering what's in DesignSafe or how to use DesignSafe, we have recently implemented a brand new version of what our Ask AI chatbot just became available this year, where we have used this retrieval augmented generation method. I guess it's sort of like a physics informed neural network, Jim. So it's not really a trained on our data, on our model. It's not really trained on our published data sets, or trained's not the right word. We have a graph database that stores all of the information from published data and from our documentation, and the LLM is used to understand what you're looking for and translate that into looking through our graph database first, and then bringing information to you. Here's what the interface looks like. In the upper right corner of our navigation is Ask AI. And then here's something I said, well, I'm interested in data sets regarding reinforced concrete. It tells you what parameters it's using, that it's going to use in our going through our graph database, builds a response, and it usually comes up with like 5 relevant data sets, and then it says something about, yes, and you can explore more data sets related to reinforced concrete using this full result link, and keep looking. So for other things. So final thoughts. Again, TAC is a very large organization. We have 220 people. We have about 10 FTE funded through DesignSafe, spread across about 30 people. But really, if the right person isn't on our funding, we can put them on for a short time and be available to help you in any way you need help. So please don't bang your head against the wall on any computational questions you might be having, any data analytics, any geospatial tools, any of that kind of thing. Submit a ticket, use our Slack. You can direct message me. Alexander Fields, shown here on the right, answering Pedro. Arduino at the University of Washington, Professor Arduino. Alexander is my colleague who works closely with me on communicating with the research, the research community. We're very responsive in Slack, and we'll be glad to help you at any time. So, and any kind of question. I don't care if I'm trying to decide what to do in grad school. Should I keep going? What should I do? Should I get a postdoc? What do you know, Tim? What was your experiences? You did startup companies. What's that like? I don't care. Ask me anything, please.
We do have one question in the chat. Are these data peer reviewed prior to publication? That was one question.
They are not. That's a great question. So We evaluated that process and capability. The cost of doing that would be enormous. For one thing, it would take an army of people to get to the number of data sets that we have published in the last 9 years. So they are not. So that's why we have these impact metrics that we showed in using a make your data count is a standard developed by the data community. And so that helps you understand the value of a particular data set. Are other people downloading it? Are they spending time looking? You can look at the files. You can get a little pop-up window and you can scan through the files without having to download them. And then you can also see how many people cited it and where that citation was, and link out and go find the paper that they cited it, and make those connections. So that's kind of how we decided, let's move forward in this direction. Let the community tell each other, is this valuable data? And also, when you're putting it out there and your name's on it, and you're a professor, your students are publishing things, you're going to spend some time thinking about what you're publishing, because it's your reputation. And if people are out there looking at your data and it's not very reusable, that reflects on you. So we found that people spend a lot of time preparing. The other thing is we have office hours. Dr. Maria Esteva herself, who developed all of these ontologies, she is available to you through a Zoom meeting every week. You can jump in with her or schedule a time if that time doesn't work for you. We provide real human in the loop, not just written answers. I've gotten on many Zooms, people writing their career proposals, people wanting to first get into using HPC and don't quite understand how to best use it. That's our job. We love it too. I mean, and it is the best way to help people is, I mean, you can read our documentation, you can talk to other people, but we're here. And you are never, ever bothering us. Please reach out. Please don't bang your heads against the wall. I wish we were in person, Robin.
Me too. It's not quite the same, is it?
Tim, I have a question. Sorry, this is Jim. Is storage, you generate a lot of numbers. Storage, I guess we got to keep an eye on that. Otherwise, it can get out of hand, right? That's an issue. How do you do the storage? People need to download their data after so many days, or?
So the thing about our storage at TAC is, compared to what everybody's used to, is pretty much, you would think it's limitless. We have hundreds of petabytes of capability. DesignSafe itself, with the data that's only private to you, that each of you have brought to us, plus what's been published. And when it's published, we make a copy of the particular files you said you're publishing. We put those over here so they're locked in, because you can version that. So we have over 2 petabytes of just DesignSafe data, and it's a drop in the bucket. We really don't. You can bring us a lot of data. We really don't worry about. We don't have quotas. We strictly enforce. Some of the data is so large. Some of the data sets, a few here and there. There's some very large hurricane data sets. You wouldn't be able to download it to your local computer anyway. Maybe if you have storage at your local university, that you might be able to put in 100 terabytes of data that somebody's published. But that's why it's at TAC, because you can use our resources, our compute resources, to do whatever analytics, any AI that you want. Mm-hmm. By the way, we're in the middle of building. Robin mentioned I'm part of our leadership class computing facility. We're building out the next big supercomputer. It's a $500 million project, and the racks are being installed as we speak. and it is a very strong AI system, as well as general compute on CPUs, but it will have many thousand NVIDIA GPUs on it.
Okay,
So,
sounds like a lot of
Mirsad, I see your question there, and I will make sure.
Sorry, Tim, it sounds like there's gonna a lot of heat that's going to be generated.
Yeah.
Yeah,
lot of heat.
thank you, Tim. Thanks.
A lot of heat will be generated. Yes. So, and you all will be able to access that brand new system when it comes online through DesignSafe and working with us. The precursor to that system, that's just a small little thing with 600 GPUs on it, is called Vista at TAC. Some of you, I think, have used it already. Certainly, Jim's group has access to it, and I think I see some familiar out, and I see Fei Ding is out there, and other people that I recognize. So I know there's people out there that have done a lot of cool stuff on our systems already that are on this call. So open source applications for geotechnical site. Yes, we have. Yeah, if you have an app that you would like to share with other people, openly, publicly on DesignSafe, the best thing to do is start by talking to me. Yeah. So Marsad, just hit me up in Slack, and we'll start a communication. We'll probably have a Zoom meeting to quickly start out, and we'll go from there and look at what's the best way to share this. And things get interesting when you start looking at how you've put something together, which is fantastic, and now you have to integrate it with authentication and access to data resources and all that. But we do it, and we have a team to help, right? We don't just throw it at you and say, here, go figure it out. Okay. We will help and help bring it to the forefront and help make it available. You bet. I think I hit my time.
You were right there. I'm going to ask
there.
one last time. Any other questions for Dr. Cockerill?
So Tim, there's also, I think, a value that is the software tools, because if the data is stored on TAC and you want to post-process or particularly create images, movies or streaming, there's a lot of, I think, useful tools that I think would be of value that I could see where there's no need to download the data. You can use, the tools directly at TAC to generate the post-process data you want for your videos or whatever, right?
Absolutely. And we actually have, TAC has, we're a pretty flat organization. Our director, the guy who runs all of TAC, Dan Stanzione, talks to users. Okay, he'll help users, right? So that's our job. We all help users. If we don't stay in touch with our research communities, that we aren't very helpful, right? We aren't going to stay on the edge and understand where you're going and be as helpful as we can be. To that end, we're broken up into small groups loosely, and we have a scientific visualization group that has about 8 or 9 people in it who are experts in scientific visualization, and that they keep the tools available and optimized and everything on our supercomputers, but they're also available to help you. If you submit a ticket and say, I need help with scientific visualization, DesignSafe isn't paying anyone in particular in that group right now. But if you said you needed help, I would find somebody, the right person in that group. They may have actually even done the type of science you're already doing, even along and understand your science along with knowing how to do the scientific visualization. And they contribute to a lot of open source science visualization capabilities and stuff too. We continue to help develop open source tools. Yeah.
Okay.
There's so much I can't explain in 29 minutes.
That's okay. No, thank you very much. I thought I'd asked. I knew the answer, but I thought it was enlightening maybe for some of the other audience to know.
Yeah, I appreciate you asking, because that did help me describe, just ask. We probably have somebody that's available to help you and maybe has even done it a little bit, but in your actual work, scientific discipline.
All right, I want to say thank you to Dr. John McCartney, Dr. Jim Ricles, and Dr. Tim Cockerill for sharing their expertise and their resources today about their sites. I am going to drop those in chat right now, just in case you've missed it. You will be receiving more information from all 3 sites and resources that we hope will help you. And again, if you have any questions, I know we ran out of time to have a lot of Q&A here, but they want to hear from you. So please reach out to them. We've shared their email several times. We will share it again. If you have any questions, they are happy to help. But thank you so much, speakers, for coming and sharing your expertise and your wonderful facilities with the researchers here today. Just a reminder, we will be sharing this presentation on NHERI DesignSafe on the Summer Institute website, as well as the NHERI ECO YouTube channel. We will be sending an email that will have resources for you, as well as a short survey that will help us continue to improve these short webinars that we are having. Well, this one's a little bit longer, but the 3 different segments that we had today. And so we just invite you to share that feedback with us, and thank you so much. And last, if I can get this to continue. For some reason it won't. There we go. If you have not registered for April 20th, we will be hearing from Converge, Hinsdale Wave Research Laboratory, Sim Center, and the Center for Geotechnical Modeling. We invite you to register using that QR code. Most of you have already registered, but just in case, if you have other people who have not, we invite them as well. So we're excited, and we just want to say thank you to NSF for sponsoring the NHERI network so that we can continue to bring you this wonderful content. So again, thank you to our speakers, and thank you for joining us today.
Yeah, thank you, Robin, for organizing this.
Thank you very much.